let's talk about power series some more and their associated radiuses of convergence. So we left the last section and we had spent a lot of time working with this first function, 1 over 1 minus x, which had a power series expansion of x to the k from k equals 0 to infinity. So we worked a lot with this, where its radius of convergence was 1, and its interval of convergence, if we checked the endpoints, was negative 1 to 1. We worked with that a lot. We were able to prove in the last section that 1 over 1 plus x, because that's just a substitution, was equal to this power series. And in one of our examples, we even proved that the inverse tangent of x was equal to this power series, negative 1 to the k, x to the 2k plus 1 over 2k plus 1, by making a connection with the derivative of the inverse tangent to this power series and then using our rules for integration of power series. We can integrate and differentiate power series because they're these infinite polynomials. And then this is one that the book did the natural log of 1 plus x, because if we were to take the derivative of that function, we would see the connection to this function and so on and so forth, and we can adjust. I made a little note here. This is how I write this power series for the natural log of 1 plus x. But Briggs-Cochran, the textbook that we're using, does a little adjustment on it, and they write it in this form. But in its expansion, I wrote out the first few non-zero terms for each of these power series, their associated radius of convergence, and interval of convergence. When we actually go in and check the endpoints, you can see for these latter two that you get some convergence at the endpoint. So those are the power series that we've worked with. But not every function that we work with is going to connect back to this function that we've spent a lot of time in the last section with, 1 over 1 minus x. Obviously, not every function can be written as a manipulation of 1 over 1 minus x through algebraic substitutions or multiplications or integration or derivatives. We got a number of functions, but not everyone can be written connected to this function. So how do we write a function as a power series, and how do we know if a function has a power series? So that's what we're going to talk about in this section. Okay, so as mentioned, we've been working with this guy, this 1 over 1 minus x, and manipulating it. And we know it has that power series representation. We should add in that's true as long as the absolute value of x is less than 1. This equality between the power series, not that first equality, the equality between the power series and the function. But how do we figure out how to represent just any old function with a power series? So let's talk about that. So if a function, let's just suppose to start with that a function does have a power series representation. If that's true, by our definition for power series, then it looks like an infinite polynomial where the c sub n's are the coefficients. So we got c naught and then c1, x minus a to the first, c2, c3, c4. So what we need to do is try to figure out how to find those c sub n's, those coefficients, because if we could find those coefficients and represent those coefficients, then we could represent the function as a power series. So that's what we're going to do. We're going to spend a little bit of time figuring out how to represent those coefficients. Okay, so to just get us started, I rewrote what I had typed out on the first screen, but if f of x has a power series representation, then we have a function that looks, a power series that looks like this, c sub n, x minus a to the nth from n equals 0 to infinity. And we could say the function is going to be equal to that expansion of the terms. And so if I wanted to figure out a way to represent, so if I want to find a way to represent those c sub n's, those coefficients, let's start by just taking the derivative of f of x. And let's see what happens. We're going to see some patterns occur. So I wrote out f of x here, and I'm going to just start by taking the first derivative. So obviously the first derivative, when I take the derivative of c naught, that's just a constant, so that just becomes 0. Then when I take the derivative of c sub 1 x minus a, I just get c1. And then just using, the power rule for derivatives, take the derivative of the next term. I bring down the power, 2 times c2 times x minus a to the first, plus 3 times c3 x minus a to the second, plus 4 times c4 x minus a to the third, and the generic nth term would be n times c sub n x minus a to the n minus 1, and then that continues. Now, I'm going to keep going. I'm going to speed up the video, and I'm going to take some repeated derivatives, and then we'll come back and talk about using those repeated derivatives to find the coefficients. Okay, so I've taken the repeated derivatives, and now we want to try to find the actual coefficients. So how do I find the coefficients? Well, the easiest thing to do here is to think about if we let x actually equal a. Think about if x equals a into any of these. When we plug in x equals a, what's going to happen is all the terms are going to zero out at that point, x equals a, for all of these, for the repeated derivatives. So if we want to actually find the c sub n's, let's plug in x equals a and see what happens. So let's do that now. Let's plug in those x equals a and see what happens. So f of a is equal to, of course, we have just the constant because all the other terms disappear. F prime of a is going to be equal to just C1. F double prime of a, let's scoot this up a little bit on the screen so we're plugging it in. F double prime of a is going to be equal to 2 times 1. And I'm going to go ahead and write 1 there. That's 1 times C1. 2 times 1 times C2. And F triple prime of a, when we plug it in, all the terms that are not constant will zero out. So F triple prime will have 3 times 2 times 1 times C3. And the fourth derivative of a, we'd have 4 times 3 times 2 times 1 times C4. And in fact, by the time we get down to the nth derivative evaluated at a, what we're going to end up having is we're going to end up having n times n minus 1 times n minus 2 all the way down to 3, 2, 1. And hopefully you're seeing that little pattern right there, that is actually a factorial. So each of these could actually be written as, so this is C naught, this is going to be 1 factorial times C1. This is going to be equal to 2 factorial times C2. This is 3 factorial times C3. This is 4 factorial times C4. And this would be n factorial times C sub n. Now, let's go ahead and just some mathematical notation, so some math facts here, or math facts or definitions that we're going to end up needing when we generalize our formula here. When we write f and we put a little n up here in the parentheses, now I think we all know this already and I actually used it above, but that is the nth derivative of f of x. So we're taking the nth derivative of f of x. So if I put a 0 right there, that is just the function. That is the, one way to think of that is it's the 0th derivative, or it is just the function itself. So that is the function, no derivatives. We also define 0 factorial to be equal to 1. And so let's go ahead and write that down in our notes as well. We define 0 factorial to be equal to 1. So if we're ever dividing by a 0 factorial, we'll remember that it is 1 and not 0. That is just a fact, a definition that we use. Okay, so we're going to utilize those. And let's now talk about how do I take these and actually solve for the coefficients. That's our whole goal. We're trying to find the coefficients. Well, notice that C naught is just equal to f of a, and C1 would be equal to f prime of a over 1 factorial, and C2, let's generate the whole pattern here, C2 is going to be the second derivative evaluated at a over 2 factorial when I solve for C2. When I solve for C3, I'm going to get the third derivative evaluated at a over 3 factorial. And when I take the fourth, went right off the screen, but the fourth, let's scoot that over just a little bit. The fourth coefficient, C4, is going to be equal to the fourth derivative of the function evaluated at a over 4 factorial. And the pattern that we're seeing right there is that if we take the nth derivative evaluated at a and divide by n factorial, we will have a formula for the coefficients of our power series. So if we have a differentiable function that we want to represent as a power series, if it has a power series representation, its coefficients are going to be the nth derivative evaluated at a over n factorial. So this is powerful. This allows us to find power series for functions. So we can find power series now. If a function has a power series representation, and I'll keep saying that because I want to talk about how we can show a function does have a power series representation, but if it does have a power series representation, then we can find it because we can find its coefficients by looking at the repeated derivatives and dividing by n factorial. So just to summarize what we just generated over in the notes, what we just generated in the notes is this: as long as we let 0 factorial equal 1 and f, the zero derivative of f, be equal to f of x. So those are the notations and the conventions that we're using. Then we have this theorem. It says that if we can represent a function, if a function does have a power series representation or expansion at x equals a, then the function is going to be equal to a power series where the coefficients are the nth derivative evaluated at a over n factorial. And I just wrote that out here. So I replaced the c sub n's with that formula we just generated, and it will look like this. So we can actually find the first, 4, 5, however many non-zero terms we want to in the power series expansion. And what we can do is we can look for a pattern to see if we can represent it as a series. Okay, this series that we've just talked about is what we call the Taylor series. So the Taylor series, and this is definitely one you want to get in your notes, and I have a reference sheet with this for you as well. But the Taylor series says that if a function has a power series expansion at x equals a, then it can be represented as such. And I just restated what we said above. So it can be written in this form. F of x can be equal to the series from n equals 0 to infinity of the nth derivative evaluated at a over n factorial times x minus a to the nth. And we could expand that out. The Maclaurin series is a very specific series. So the Maclaurin series is a Taylor series. It is just centered at 0. So this is a Taylor series centered at x equals 0. And because so often we do look at functions where they're centered at 0 and write their power series expansions, it gets its own little name. It's called the Maclaurin series. So you can see here that this is just the same definition, except a is 0. And so we're looking at the nth derivative evaluated at 0 over n factorial for the coefficients. And of course, instead of x minus a on each of the terms in the power series, we just have x minus 0. So x to the first, x to the second, x to the third, and so on and so forth. How will we know what functions actually have a power series representation? How can we prove that they do have a power series representation? Because if they have a power series representation, now we know how to find that power series representation using our Taylor series. So if a function does have a power series representation, then it has to be equal to the limit of its partial sum. So what's the partial sum? Well, we call the nth order Taylor polynomial that is, by definition, the partial sum, the first n terms in the power series representation. So it would be a finite with n terms, finite power series, a finite series that goes out to the nth term. And therefore, the function is the sum of its Taylor series as long as the function is equal to the limit of this Taylor series as n goes to infinity. So as we add more and more terms, if the function is equal to the limit of that Taylor polynomial, then we would say that it has a power series representation. So what does that mean? Well, if we use the Taylor polynomial to approximate the function, so if we stopped at the nth term, then the remainder of the terms would be the difference between the function and the first n terms that we use, the Taylor polynomial, the nth Taylor polynomial. So this remainder right here is really what we think of as the error. That is the error between the Taylor polynomial, a partial sum, if we stopped at the nth term, and the actual function, or the error in using n terms to approximate the function. So it follows that the function is just equal to its Taylor polynomial, the nth Taylor polynomial, plus the remainder, or the error, when we stop at the nth term, so the rest of the terms to infinity. And then we have this theorem. If a function is its nth Taylor polynomial plus the remainder in using the nth Taylor polynomial, and that remainder goes to 0, that means the error goes to 0 as n goes to infinity, then a function has a power series representation. So that's what it means. Now, let me end this video by saying this. It is not actually very easy to show that this remainder, oops, let me grab the wrong pin. that this remainder goes to 0. That can actually be a fairly difficult process that we're not going to examine in this course, in the scope of this course. What we're going to do instead is just assume that our functions have a power series representation. So the functions we're going to look at, this will be true for the functions that we're going to look at, true for functions we look at. But we're going to work more on the actual process of representing a number of functions by power series, and then using those power series to answer greater questions about those functions. Like this question. This goes all the way back to the very end of our integration unit when we were talking about how we can't actually integrate every function. In fact, a number of functions that we want to look at that we would like to integrate don't have elementary antiderivatives, so we can't use our technique for integration if we want to, our techniques for integration, because we can't find an antiderivative. And that is true of this one. This fairly simple exponential function, we do not have a way to integrate this. So what do I do? How could I figure this out? And here's where we're going to head, and I will leave this for the next video. Here's what we're going to do. We're finally going to be able to talk about what we can do with functions that we couldn't find their integrals of, that we couldn't find an elementary antiderivative. How do we actually integrate something? Well, what we're going to do is we're going to use a power series. We're going to find a power series that will represent this function, and then we know how to integrate power series, so we can integrate the power series, and then we can actually come up with an estimate for this integral. So that's where we're headed. We're going to do that on the next video, but we've finally been able to come back around and connect our functions, what we did with functions and integration, now to what we've been working on and all the skills we've been building around series and into power series. So stay tuned, and we'll do this on the next video.